Hi there, my name is Tatiana Petrache, and I'm going to present you the Lambda architecture for big data analytics, or in other words, the evolution from traditional data warehousing systems, collage data, towards modern scalable data systems, which I like to call wide format data systems, as they offer a 360-degree view of the businesses. In the next minutes, I'm going to discuss about the following points. I'm going to describe the Lambda architecture, mention some of the most important pros, cons, and some issues, describe the technology behind the demo, which is Apache Spark along with Apache Spark Streaming, show you the fun part, which is the demo, and share some of the lessons I learned. It is a very well-known fact that traditional data systems cannot keep up with the current demands when it comes to getting the right answers at the right time, which is immediately, while implementing the following vital properties: human fault tolerance, horizontal scalability, low latency reads and updates. In order to get the right answers, a sine qua non condition is to consider the entire dataset, wide format data, as input, as opposed to querying collage data from a data warehouse. As Nathan Mars stated in his book, the Lambda architecture solves the problem of computing arbitrary function on arbitrary data in real time by decomposing the problem into three layers: the batch layer, the serving layer, and the speed layer. To better understand this architecture, let's say you get an unusual request from one of your customers. He tells you that Cookie Monster has been continuously eating cookies since Monday, and he would like to know how many cookies he ate until now. You could query the data warehouse and do a select to get the total number, and this number can be the number of cookies from the right hand side of the slide. But you know that this is not the up-to-date number of cookies, as you don't have the data from the last 5 hours in your batch view. In order to compensate for those last few hours of data, you need to add a speed layer and merge the real-time view with the batch view. Now you can answer the question. In other words, we have three equations to solve. Firstly, get the results from the batch view, then from the real-time view, and finally merge those two. Of course, once the data makes it through the batch layer into the serving layer, the corresponding results in the real-time views are no longer needed. Furthermore, the advantages that the Lambda architecture offers are numerous, but just to name a few. Immutability is one of the fundamental advantages of this architecture, and it emphasizes retaining the input data unchanged. Also, we could mention the real-time querying, recomputation algorithms, which are inherently human fault tolerant, and scalability. The low points mentioned in most of the articles addressing this architecture are related to the complexity of the implementation, the one-way flow, as immutable data flows in one direction, into the system. Lambda doesn't transact and make per-event decisions on the streaming data, nor does it respond immediately to the events coming in. Also, reliance on eventual consistency makes it impossible to feed data quickly back into the batch layer. It's important to mention also the issues I confronted myself while configuring the Scala project using Maven. First error I got was related to the two different versions of Jetty getting included, and as a result I had to add Jetty related jar exclusion filter in pom.xml. Moreover, the Scala IDE sets the latest Scala version as default for the compiler, and I had to change that to 2.10, which is the actual Scala version from the Cloudera Quickstar VM. As I mentioned in the pros cons slide, the Lambda architecture implementation can become pretty complex, as you'll have to implement and maintain the same business logic in two different systems. But Apache Spark came to the rescue, the framework being capable for ETL tasks and streaming processing. Now a few words about the Apache Spark framework. Spark has clean and easy to use APIs and comes with a Spark shell, which allows for fast prototyping of logic with business users. The fundamental programming abstraction is called Resilient Distributed Dataset, which offers two types of operations: transformations and actions. The really cool part in the demo was Spark Streaming, as I was able to reuse the same aggregates from the batch application in the real-time stream. Spark Streaming receives live input data streams and divides the data into batches, which are then processed by the Spark engine. The high-level abstractization in Spark Streaming is called Discretized Stream or DStream. Now let's continue with the fun part, which is the demo. The goal of the demo is to analyze broken URLs from an Apache access log. The dataset I use has around 1.5 gigs and it represents the access log from the Star Wars Kit demo. This is the combined log format of the Apache access log, and we are interested in two attributes: the request line from the client and the HTTP status code sent from the server to the client. The first step is to write a function to embed the business logic, namely the count of the broken URLs requested by the client. Let's test the logic using the Spark shell. We'll begin by reading the input file into RDD, which is a resilient distributed dataset that represents a collection of items distributed across many compute nodes that can be manipulated in parallel. Next will be the pattern to match the request from the client, but we only want to keep the URL out of the request. We'll continue by applying the following transformations. We'll keep only the records with HTTP status 404. Get the URL, convert the elements of the collections into strings, and count the URL. Lastly, we'll print the results. It's also interesting to compare the results with the input file. Let's take them line by line. In the first line, we have a result since the HTTP status is 404. Same for the second line. For the fourth line, we don't have any corresponding result as the HTTP code is 200. The URL from the last line also appears in the results as the HTTP code is 404. As you can see, we added a common function to the Scala project. This is the same code as the one from the Spark shell. Next, I'll show you how to implement the batch layer. We'll start by initializing a Spark context to execute our code within a Spark cluster. We'll use that Spark context to read lines from the access log into RDD. Then we'll execute the common function. Finally, we'll save the results into a file. We'll use the coalesce function to output all the results into one file. Next, we'll run the application. You need to specify the following configuration and parameters in order to execute the batch code. Run the code. You can see in the console that the initial file has been split into many subfiles. The reason behind this is that by default, Spark casts the file into blocks of 32 megabytes. Next, refresh the project and check the contents of the output folder. You'll see that there is only one file with the results. Open the file and analyze the output. We'll continue with the speed layer. We start by initializing a streaming context. We'll also specify the checkpoint that will save intermediate data. Then we call the common function and print the current count. We also calculate the running counts using the update state by key function, which accepts two parameters, a data type and a state update function that basically updates the running count based on the previous state and the new values from the stream. Next, we are going to execute the streaming application, but first we need to run netcat, the data server which will periodically feed the streaming application. Run the application and make sure you specify the same port number as parameter, which is 9998. Copy and paste the log lines periodically into the NC terminal and check the Eclipse console. You'll see that with each line that was added and sent over the network socket, both the current and the running counts get updated automatically. Repeat the same process to convince yourself and copy and paste some more lines. As you saw, the speed layer fixes the problem concerning the low latency updates. In order to obtain a real-time data system, we need to compensate for the last few hours of data that came in while the precomputation was running. Another key aspect that needs to be touched upon is that both your views must be merged together to achieve the proper results. In order to simulate the query layer, I have initialized a new Spark context and hard-coded some results from the batch application. We'll create a new RDD with two lines. Next, we'll merge the results of the state stream that keeps the total count of the streaming data with the historical data using the union operation. Of course, we need to print all the results to the console. Now it's time to see the query layer in action. The netcat is already running, so all we need to do is to check if the query application is using the same port number. Next, feed the new application by copy and pasting long lines into the NC terminal. Note that the total running count has been successfully updated. You can repeat the process several times and monitor the results in Eclipse. Finally, I would like to mention some key takeaways that I've learned while building the demo. First of all, the Lambda architecture is not ideal for everything. Always research before writing the demo code. Come up with an analogy when explaining concepts. This will make life a lot easier both for you and your readers. Find some concrete use cases. This will give you the real satisfaction as you suddenly realize that you're doing more than a homework assignment. Read on. As you have already figured out, this is not the only architecture available in the big data world. There are many more, such as the CAP architecture, the ZOT architecture, the YOT architecture, which is the Internet of Things architecture, the hybrid Lambda architecture, and so on. Last but not least, be enthusiastic, and the learning will come naturally. Thank you.